Hey everyone, welcome back and let's write some more Leetcode today. So today let's solve the problem stone game, and honestly this is a very interesting problem. In fact, it's so interesting that there's around 10 problems, 10 variations of the stone game problem on Leetcode. And believe it or not, we can skip directly to the coding section where we can go ahead and just return true, run the code, and you can see it beats 97%. So if that's all you were looking for, if you just want to pass this problem on Leetcode, there's your solution. But in seriousness, let's go back to the drawing board and understand this problem. Because obviously in a real interview, they'll probably know that you just memorized that line of code, if you even do get this exact problem. But obviously you could get a variation of this problem. There's many variations, so let's understand it. So we have two people, Alice and Bob, A and B, two people, and we're given a pile of stones. The pile of stones is given in an array. So for example, this could be one pile. The length of it is always going to be even, which is very important. And every stone, each stone is basically a value in this array. Each stone is going to have a positive value associated with it. Another thing, the total sum of all the values in this array are going to be odd, and that's also going to be important because what the problem is about is Alice and Bob are going to be taking turns, choosing a stone from this array. The restriction here is that Alice is going to go first and Bob is going to go second, and each of them can only choose from the beginning or the end of the array, right? From the beginning or the end of the array. So if Alice takes 5, then this is our array remaining, and then either Bob can take the 3 or Bob can take the 5. And we really want to know who can get the highest score. So the question we're asked is, assuming Alice and Bob both play optimally, return true if Alice wins the game or false if Bob wins the game. Now, from what I showed you a second ago, we know that Alice is always going to win the game. And we happen to have a big O of one-time solution that can solve this problem. So do we really need to do more? Well, at the very least, you probably need to understand why the O of 1 solution works, because you'll probably be asked that in an interview if you do use that solution. First of all, since we know that the number of stones is even, right, the length of piles is even, that means both Alice and Bob are going to get an even amount of stones, and we know that the total of this array is odd, right? The sum of this array is odd, so at least one of them has to win, right? If you take half of the array and just split it randomly, one half is going to be bigger than another half no matter what, right? One of the halves has to be bigger because the sum of it is odd. So we know that Alice goes first, and because of that, she's always going to win the game. And that's pretty obvious if you have an even length array of just 2 elements, right? Because in this case, there's just 2 elements. Of course, Alice is going to be greedy and pick the bigger one, so she's going to get 4. Bob is going to be left with what's remaining, which in this case is 3, so Alice is going to win in pretty much every time in that case. So then you might think, well, is Alice always going to play greedy? Because right now Alice has, given this array of 4 elements, Alice has 2 choices. She can pick the 5 or the 6. Now, if she picks the 6, then her total is going to be 6. And then Bob has, this array of 3. Bob can either pick 5 or 100. Of course, Bob is going to pick 100. And, by default, there's 2 elements left. Bob has 100 already, so Bob wins. So in this case, being greedy for Alice doesn't work. So Alice can pick 5 first. And then, of course, Bob is going to pick 6. And then Alice can choose the 100, right? So being greedy doesn't always work. The question is, why is it, though, that Alice can win every single time? Well, remember, we were told that both Alice and Bob play optimally, so we don't know what optimally is. Being greedy does not mean optimal. And how many different choices does Alice actually have? Like, how many different, combinations could there be of Alice choosing stones? Well, Alice has 2 choices each time, right? And the length of the array is, let's say, n. So really the time complexity is going to be 2 to the power of n. That's how many possible ways Alice could choose stones, pretty much. And so among these, we're just asked, at least one of these ways, whichever way happens to be optimal for Alice to play, at least one of these ways Alice has to win, right? Regardless of what Bob does. If Alice chooses the stones optimally, then Alice has to win at least one way, and that's guaranteed to be true. But why is it true? Well, we're going to extend that idea of two elements, right? If we have two elements, it's simple that Alice is going to win. Alice is going to pick the bigger number, and then she's guaranteed to win. Well, that idea does work in four elements as well. Think of it this way. If Alice picks 6 first, right? She has two choices, 5 or 6. If she picks 6 first, then she can guaranteed pick this element as well, this one element as well. Why is that? Because Bob is going to have two choices. Bob can either pick the 5 or the 100. So if Bob picks the 5, then this element will be available for Alice to pick. If Bob picks the 100, then this element will also be available for Alice to pick. But in this case, 1 plus 6 is not the solution, right? 7 does not mean Alice wins, right? That's not enough. But remember, Alice chose 6 initially. Alice could also choose 5 as the first element. So if Alice chose 5 as the first element, then Bob could either pick 1 or 6, but then Alice is guaranteed to be able to choose this if she wants to. She doesn't have to, but she can because it will be available for her. Basically, we saw that Alice has a guaranteed way of getting 5 and 100 if she wants to, and then this would be the total that she could get if she does that. She also has a way of getting 6 and 1 if she wants to, a guaranteed way of doing that, and then this would be the total. We don't know for sure which one of these combinations that Alice could pick is going to be the one that gives a greater total until we actually run the calculation like I just did. We don't know which one is going to be the solution, but we know at least one of these has to be greater than the other. In this case, we see 5 plus 100 is greater than the other. We know this because the total sum of this is going to be odd. Both of these cannot be equal, right? One of them has to be greater than the other. And using this idea, we can kind of formally, this isn't like a formal proof, but it really gives you the intuition of exactly why Alice can always win. Let's extend this idea that I showed you to a more generic sized array. So let's say we had a generic sized array. This is index 0, this is index 1, 2, 3, etc. until n, right? And we know n is going to be an odd index number because we know we're always going to have an even number of elements, right? We're starting at 0, so this has to end in an odd number. Basically, what I'm about to show you is that if Alice wants to, she can guarantee herself to be able to pick every single even number in this entire array, if she wants to. She also has a guaranteed way of picking every single odd number in the entire array. She can pick every even number or every odd number if she wants to. And we know for sure that the sum of even is not going to be equal to the sum of the odd elements, right? We know that for sure. It cannot be that that one half of the array is equal to the sum of another half of the array because the total sum of the array is going to be odd. So if she has a guaranteed way of picking even or odd elements, if she wants to, then whichever one of these happens to be greater, Alice can play in such a way that she picks the one that happens to be greater. So that's the idea. And how exactly can Alice pick every odd element or every even element, you might be wondering? Well, that's the simple part, actually. If she picks, right now we see that the left index is 0, that's an even number. The right index is n, which we know is initially going to be an odd number. So if Alice, let's say, picks the 0, then the choices for Bob are either an odd number here or an odd number here, right? So if Bob picked the odd number here, then Alice could pick the even number here. Or if Bob picked the odd number here, then Alice could pick the even number here. So basically, since Alice is the person that has the first choice, Alice can control how the game is played. Alice can make it so that she gets all of the even ones, or she can get all of the odd values as well if she wants to. And so that basically proves that Alice, since she goes first, and if she plays optimally, she's going to win every single game. So I hope you enjoyed that O of 1 solution for this problem. It's very rare that we have a constant time solution. So that's what's really interesting about this problem. I really like this problem. But there's another solution for this problem, What if they changed the problem slightly, and what if they said that the total sum of the input array is not necessarily going to be odd, it could actually be even? In that case, is it always going to be true that Alice wins every single game? No, it's not going to be necessarily the case, because it could be that one half of the array is equal to another half of the array. So even if Alice picks every odd element or every even element, it could be the same value as what Bob picks, so they're equal. That means Alice isn't going to win every single game. So if you got this as a follow-up question, or if you just want to know a different way of solving this problem, let's try to understand the dynamic programming solution of this problem. So first of all, let's start with what we actually started with when we first talked about this problem, the brute force, right? We know that how many different combinations could Alice actually pick from these piles? Well, she has 2 choices each time, right? And the length of the array is n. So the brute force is there's 2 to the power of n different ways for Alice to pick stones, right? What would that decision tree of her choices actually look like? Well, initially, so of course she could pick the element at index 0, or she could pick the element at index 3. Each of these choices would give her a total of 5 and 6 respectively, right? What we care about, what Alice's total is, that's what we're going to be keeping track of. We know that Bob's total is just going to be the total of the array minus Alice's total, so we could calculate that easily if we wanted to, but we care about maximizing Alice's, so that's what we're going to be keeping track of as the total value. So what makes this a little bit difficult is we don't only care about Alice's choices, we also care about Bob's choices, and Bob is technically also going to play optimally, but that's not really a main factor for us. So of course, if Alice picked 0, then Bob's choices are either 1 or 3, or if Alice picked 3, Bob's choices are either 0 or 2. In both cases, though, the total is going to stay the same for Alice, right? Alice is still going to have a total of 5 in this case, and Alice is still going to have a total of 6 down this path. And I hope this gives you a general idea of the brute force solution. We'll continue on just one of the paths for this tree because I don't want to spend too much time on it, but you can probably see why this is 2 to the power of n. The height of the tree is going to be n, and each node we have 2 choices, so that's kind of where we get 2 to the power of n from. Let's finish up the tree and then understand how we can apply DP, dynamic programming, to this problem to actually get the time complexity to be down to n squared rather than 2 to the power of n. And the way I'm going to be implementing this is actually by using recursive caching, dynamic programming with caching, rather than a true dynamic programming solution, just because it's a little bit easier to understand. But going down this path, we know that if Alice picked 0 and then Bob picked 1, Alice can either pick 2, index 2, or index 3. Of course, we want to go down this index because that gives us a total of 105. Of course, Bob doesn't even have a choice anymore because we already picked 0, 1, 2, so the only remaining element is 3. So in that case, our total is going to be 105. That's for Alice, right? Alice is going to have 105. So how do we know if this amount is enough for Alice to win? Well, we could compare it. We could check, is Alice's amount greater than Bob's amount, right? So that's how we could implement this recursively. And this solution is easy to optimize with dynamic programming. Basically, you want to find a way to eliminate repeated work. The main way, so initially we start out with an array that we can pick any elements from, right? But if Alice picks this element, then we have a subarray, right? We want to know, can Alice still win the game with this subarray, right? What's the max amount that Alice can get from this subarray? So the way we can cache is by using 2 values, a left and right index for the array, right? This will be our sub problem, but I think the way that we're going to be caching this will be easier to understand when we actually go into the code. So let's go ahead and do that now. The time complexity will be n squared, because how many different combinations of left and right indexes can we get from this input array? Well, there's n possible values we could have for the left index and n possible values we could have for the right index. So n times n is n squared. That's how we're getting n squared for the time complexity of this problem. So without further ado, let's jump into the code. Okay, now let's get into a more heavy solution than just returning true for this problem. But like I said, we're going to be caching to speed up this problem. So we're going to initially start out with the brute force and then apply caching to it. The way we're going to be caching is we want to basically, for a particular subarray of piles, and we're going to determine a subarray by taking the left and right index of the array to determine the subarray. And for that subarray, we want to know, okay, what's the max Alice total we can get if she plays optimally, right? So if we can, do this, then we can efficiently solve this problem. But now let's get into the actual recursive part of this problem, the brute force, and then apply caching to it. So there's two parameters we're going to pass in, the left and right index, because that kind of determines what elements are remaining for the array, right? What elements can Alice actually choose from? And you can see that I have a function defined inside of a function. That's just so that we don't have to pass every variable like piles and dp into this function every time we call it. That's just my preference, but you can do it differently if you would like. So now we're doing this recursively. What's a base case? Well, the first one is if we have no more elements to choose from, right? Like what if we have gone through every single element in the array? How will we know if we have done that? Well, if our left index passes our right index, right? If our left index becomes greater than our right index, which normally shouldn't happen, until we have reached every single element in the array. If that does happen, then we can return 0. If there's no elements to choose from, what's the max amount that Alice can get? Of course, it's going to be 0. And by the way, that's what our DFS function is going to be returning. The max Alice total from this array. Right, you can see that what this function is returning is the same as what this this hash map up above that we've defined. It's going to be storing the same value, right? The max Alice total, which is why we're using this to cache the result of this function so that we don't end up calling the function with the same parameters twice. Right, and that's going to actually be our other base case. If this left-right pair of values has already been called, or if it's already stored in our DP hash map, then we can go ahead and return that value. We don't have to recompute that work. So that's what we're going to be doing here. If this left-right pair has already been computed and stored in DP, then we can immediately return it. That's what we're doing here. Otherwise, we have to do the recursive part. So if Alice is making a choice, Alice can pick the left element or the right element. So if Alice picks the left element, then what are we going to be calling recursively? Well, if Alice picks the left element, then we're going to set left to L+1 and leave right the same, because then we're saying that, okay, this is the remaining subarray, right? For Bob to choose from. If Alice picked the opposite case, if Alice picked the right value, the right pile, then left would stay the same, but we'd take right and then subtract 1 from it, right? Because that element is no longer available, so we're decrementing our right pointer. So these are the two choices that Alice can make. And we want to know which of these two choices is going to maximize the amount that Alice can actually get. But don't forget about one thing. This function is about returning what the max amount Alice can get, but we actually have to make Bob decisions as well, right? Bob has choices that he can make as well. And how do we know if Alice is the one choosing or if Bob is the one choosing? Well, it's basically about how many elements are remaining. If we have an even number of elements remaining, that means Alice is the one making the choice. If we have an odd number, right, like basically if Alice picked one of the elements, then we have an odd number remaining, so then Bob is the one making the choice. So let's just basically determine if the length is even or odd. So we can do that like this, just by taking right minus left and then mod it by 2. This is just a ternary operator, just determining if we have an even or odd number of elements. And then we can use the result of this to basically clean up the code a little bit. So basically here we want to know, okay, if Alice picked the left amount, how much is it going to contribute? So piles at index left. The reason I'm doing this is because we know that Bob's choices aren't going to contribute to the result of this function, only Alice's are. So if Alice picked left, which Alice can only do if the length is even, right? If it's even, then left is going to be assigned to piles of left. If it's non-even, else is that case, then this is going to be assigned to 0, because that means Bob is the one making a choice. This probably is going to look a little bit confusing until we actually finish the function, so you can take your time in understanding this. So we're just copy pasting this. So same thing, left and right, these are the choices. And so using these values, left and right, we can actually finish up this function. So if the person made a left choice, this is the function for that, plus left. And this, if they made a right choice, is this plus right. So remember, we want to return the maximum of these. So we can do that by just taking the maximum of these two. And once we take the maximum of those, we're going to go ahead and put it in our cache and then return that value, right? So left, right is our key for our cache, and then we can store the maximum inside of it. And then we can go ahead and return DP at this. So I know this probably looks a little bit confusing, but just so you know, what we're mainly doing here with the left and rights is about the return value here, right? We want to return what's the max total that Alice can get. So every time Alice is the one making a choice, we want to add that to the return value. But every time Bob makes a choice, we want what Bob picks to be 0 because we don't want Bob's choices to contribute to the return value. So even is basically when Alice is making a choice. If it's odd, that means Bob is the one making a choice. So when it's Bob, left and right are going to be 0. So then here in this computation, you can see that left and right are 0, so they're not contributing to the result. But if Alice is the one making a choice, then left is the value of the stone she picked, and right is the value of the stone she picked. And then these recursive functions are the amount that Alice is going to get from the remaining stones. And of course, she has two choices, right? Left and right. We want to take the maximum of these and then return that because we want to know what max value Alice could actually get. So that's kind of the logic of this problem. Last thing we have to do is just call DFS starting from the beginning of the array and from the end of the array, which is the length of piles minus 1. So then we can return that value. And that's the entire logic of the code. Let's run it to make sure that it works. And as you can see, it does work. It's pretty efficient for a dynamic programming solution, but you can see it's definitely not as efficient as our just simple solution where we just return true. So yeah, you can see that the return true solution is definitely a lot faster. But I really hope that you learned something from this problem because it's a very interesting problem. I hope this video was helpful. If it was, please like and subscribe. It supports the channel a lot. Consider checking out my Patreon where you can further support the channel, and hopefully I'll see you pretty soon. Thanks for watching.